the first formula I want to talk about. Yeah, counting, yes. Okay. I want to begin with the following. Okay, somebody's microphone.
What if I'm going to type in the S?
Okay. Well, let me show you the picture first. Suppose you have two sets, A and B. Okay, and I'm going to use a notation for if this means the number of elements in A. Okay, so you know the notation A is this is called the union of two sets, right? And this called the intersection of two sets. Okay, so the formula says that the number in the union of two sets, okay, is going to be the number in the the number of elements in set A and the number of elements in set B. But you have to subtract the elements in the intersection of two sets. The reason is if you just count the elements in set A and you count the elements into B, add them together, those in the intersection part are double counted, so they have to subtract them. Okay? Then you get the number of elements in the union of these two sets. But how about the three? Okay? If you have a three, you have three sets, A and B and C. Things become more complicated. Okay? If you want to, count the number of elements in the union of the three sets, of course you want to add them together, right? But in this case, you have to subtract. You have to subtract the elements in the intersection of the three sets. And finally, you have to add the elements in the intersection of the three sets. So it's pretty complicated. Now, to prove that, how do you prove that? Okay, it's hard to, roughly speaking, when you count them, right? A plus B plus C. A plus B plus C, those intersection part are all double counted, right? So you have to subtract them. But if you subtract them this way in the intersection of three sets, actually, one minus, actually you count three times to subtract, and you are lose one, so you have to add the intersection part. Okay, so maybe it will be a little bit easier to see that if I denote this one the X, that's Y, Z, U, X, Y, Z, U, V, W, and the one in the middle I call the K. Okay, so the union of those two is going to be X plus Y plus Z plus U plus V plus W plus K, right? Those how many? Yeah, they add them together.
Can I eat this?
All right, now this is left hand side. The right hand side, A is going to be X plus U plus W plus K, okay? And B is going to be Z plus U plus V plus K. And the C is going to be y plus v plus w plus k. So you subtract, of course, you will see that you have, in a uv, like you have w there, double v there, w there. So you have to subtract the intersection of AB. Intersection of AB is u plus k. Intersection BC is v plus k. The intersection of CA is w plus k. Then you delete one w, delete one u, delete one v. Unfortunately, if you're doing like that, there will be 3k, 1k, 2k, yeah, 3k there. All the k is gone. So you have to add the k back. K is the intersection part. Okay? So then you get x plus y plus z plus u plus v plus w plus k. Okay? So this is a nice formula. This for us to, we can use that to count some numbers. Okay? So here's the question. Okay? How many integers from 1 to 2,700? We also, inclusive, they have at least one prime factors in common with 2,700. Right? What does that mean? 2,700, I can factor it. It's going to be 27 times 100. 27 is going to be 3 cubed. Right? And 100 is 10 square. So 2 square and 5 square. Right? So those are the prime factors are 2 and 3 and 5. So the integer at least has one prime factor as in common with 2,700 means we consider the integer was which is divided by 3 or 2 or 5. Maybe divided by 2 and 3, but at least divided by one of the factors. Okay, so the question is how many integers, okay, between 1 and 200, right? And then divisible by one of those prime factors. One of them, at least one of them, that means it could be both, right? Can be divided by 2 and 3. Could be divided by 2 and 5. Could be divided by 3 and 5. Okay, or it's divisible by the 3 factors. So this is hard to do that directly. So the idea is that I'm going to consider those integers less than 2,700 divisible by 2. Okay? And I let B to be this divisible by 3. Okay? Then C are the integers divisible by 5. Okay? So we actually trying to find the elements in the union of these two sets. It means either in A or B or C. When you say in A, it's divided by 2. If it's in set B, divided by 3. If it's in set B, C is divided by 5. So you just need to find that. Okay? And according to the formula, okay, this is going to be the sum of this minus this, minus this, minus this, and plus the intersection of these three sets. Okay? Now, how do I calculate the number of elements in the one set? The number of elements in one set, you just need to look at, for example, I just give an example, okay? suppose this one. This means that the integers divisible by divisible by 2 and 3. So 2 and 3 will be 6. Right? Yeah. So then how do you calculate that? 6 times k less than 2,700. So k is going to be 2,700 divided by 6. Yeah. And then, yeah, you can simplify that. You get the integers, okay? Yeah, this time it's integer. Actually, what you're going to get usually is this notation. If it's not integer, you take the integer part. The reason is, it could be k is less than or equal to some number in decimal form, but then you get rid of the decimal, the digits after decimal point. So the integer part will be denoted by this. Okay, but here, this is going to be, this is divisible. Actually, is 27 times 100, right? Divided by 6. 3 times 2. So actually, it's going to be 9 times 50. Okay, so 450 there. So actually, there are 450 integers divisible by 6. Right? So using this idea, then we can have 2,000 divided by 2, the integer part, divided by 3, and 2,000 divisible by 5. Okay? Then minus divided by 6, and BC, B and C is 15. Then AC, it's going to be 10. Okay? Then finally, the intersection of 3 sets. We have to multiply by 2 times 3 times 5. So after the calculation, you will get the answer which David already got. Okay? Okay, it's 1980. So, yeah, let me repeat the formula, okay? The number of elements, the number of positive integers less than equal to capital N, and divisible by P is going to be N divided by P, and take the integer part. The integer part of N divided by P, but this could be a decimal point, decimal number, okay? Why this is true? Just do the division divided by K. Divisible by P means this is just multiple of P, right? So PK are those such numbers, and this should be equal to less than equal to N. So then K is less than equal to N over P, right? So the possible value for the K is going to be 1, 2, 3. And then the last one, if it's not an integer, you just take the integer part. So actually, the total number of such numbers, is going to be N over P divided by P, and take the integer part. Okay? Okay, this is why. This is the proof. Okay. My next question is about about counting also. in how many ways can Henry, right, Stephen, John, Robert, yeah, I have too many people here, and yeah, this is May, and Connie line up, right, so that no two of the three boys are next to each other. Yeah, we have three boys, Harry, Stephen, John. No, how many? Those are the boys. We have five. This Robert is five. The boy is there. Okay, I'm going to change the name here. Yeah. A female name, right? Rosary. Okay. So no two of the three boys are next to each other. Yeah. Connie is boy's name. Okay. Anyway, so we just assume three boys, three girls here. Okay. How to count them? You know, we have to look for possible patterns, right? In order to make sure no boys, no two of three boys are next to each other. So the possible pattern will be boy, girl, and boy, girl. That's one of the pattern. Okay, and then begin with a girl also. Girl, boy, girl, boy, girl, boy. Okay. So those are typical. But it's possible two girls can be next to each other, right? Right? If two girls next to each other, then it can be boy, girl, and boy, and girl, and girl, and boy. Right? So those two girls can be moved to the front. Okay? Any other possible patterns you can think about? Suppose if you begin with a girl, I don't think you are going to make it. So for the second case, two girls next to each other, you must begin with a boy. Okay. So this is yeah. So those are four possible patterns. Okay, you BGB, GGB. Okay, so we already have one. Okay, so you have four possible patterns, and if for each pattern, how many arrangements? For each pattern, how many arrangements? You're going to have a 3 factorial and 3 factorial, many possible arrangements, because you can permutate 3 boys and 3 girls. Okay, and the total you have 4 patterns for each pattern. So this involves several steps, right? To select the students in a row, putting them in a row. So first of all, you choose each fixed pattern, okay? But you have one of them. So you have 4. You have 4 possible ways to do that. Okay. So step 1, you have 4 choices. In step 2, you permutate the number, those 3 boys. So you get 4 factorial, 3 factorial. Then step 3, you permutate 3 girls. Okay. So the answer is going to be 144. Okay. Okay. Now flip a coin 9 times. Okay. What is the probability that exactly 2 flips will be hit? Or 2 or 3 doesn't matter. Okay. All right, 9 times, right? Coin. 1, 2, 3, 4. All right? Every time you record it, either tail or edge. But what is the probability that you are going to get exactly 2 heads? No more than 2 heads, not less than 2. Eric? Okay. For the probability, right? You know that first of all you have to figure out the denominator, the number of all possible outcomes. The number of possible outcomes is in each step you have 2 choices, right? So that'll be 2 to the 9th because you have 9 flips. Each time you have 2 choices. So 2 choices, 2 choices, 2 times 2 times 2. That's 9 twos. Right? All right. What is the probability? Anyone else? Alex Song? Hmm? Yeah, this 2 could be any of the position, right? Age, for example, age. Okay. So you have to change the problem to another problem to figure out the number. Right? So the rest of the T. But that could be in many different locations. So think about that. You have 9 positions in a row, right? The first one called 1, second one called 2. Okay, the question is, how do you choose, right? You have to choose choose 2 of them, right? To give them H. That's it. The rest of them get a T automatically. But you can count directly. You can say the first one, then yeah, you can choose like that. 1 pair, 2 pairs, 3 pairs. That's not efficient way, but you can do like that. So then you start from here. Okay? But what I want to say that this is going to be 9 factorial over 9 minus 2. 7 factorial, 2 factorial. Okay, it's just equivalent to the problem selecting 2 students out of 9. Okay, if there's 2 students out of 9, how do you know the difference? Well, in the second place, I call the brother 2, right? Third place called brother 3. But anyway, you're going to select 2 out of 9 brothers, right? Right? They have different names, the brother 1, brother 2, brother 3. Okay? Then brother 3 and brother 5 are selected. Okay. Then those 2 get H. The rest of them get a T. Okay? So the number of the pairs of the brothers is going to be 9 factorial over 7 factorial or 2 factorial. Right? Then you simplify it. Right? So you get the answer. So if you simplify, you will get 8, 9 times 2. Right? Yeah. So that will be 4. And so it will be 2 squared. It's 9, 2 to the 7th. So this is the answer. Okay, 2 to the 7th. I think 2 to the 7th is going to be 128, right? Right, another one. A ball contains 10 jelly beans, 4 red. Yeah, let me draw the picture. Okay, this is a ball. Okay. 4 red jelly beans and 1 blue and 5 white. Okay. If you pick 3 jelly beans from the ball at random and without the replacement, just pick 3. Okay. What is the probability that exactly 2 will be red? What is probability that exactly 2 will be red? Okay. Wow. Any idea? You don't know? Nope. It's principal counting, right? First of all, you figured out the denominator, okay? What is the denominator? Denominator, in my opinion, is going to be 120. Very cool. You're smart. Can you give me the answer? So far, I haven't got a correct answer yet. Okay, do your best. I'll give you half more minutes. All right, so we pick up 3 beans, right? Jelly beans. Doesn't matter the order in this problem, I think. You can count their order, but if you don't want to count them order, then yeah, it's better not to count them order, okay? You will see that. So the number of all possible outcomes will be total, how many of them, right? Total, there will be 10 beans there. So 10 beans, 10 factorial. Okay, if the order doesn't matter, pick up 3. There will be 7 factorial divided by 3 factorial. Okay. If we don't count the order. And now, if you don't count the order, what do you mean? You can only have, you can put the red beans on this side and then other beans, right, in this form. Okay, always regroup them, right? So, in order to get the desired outcome, you will, okay, yeah, in order to get it, you will have to select 2 red beans first, okay, out of 4. Okay, so there'll be 2 red beans out of 4. Okay, I'm not gonna, yeah, this is gonna be multiplication. Then for another box, just only pick up 1, right? And then you have how many beans, other beans right there? 6, right? So 6 factorial, but you have to pick up 1 of the 6 beans, which is 1 factorial, 5 factorial. So it's just 6. Okay. Then you multiply this out, and this will be 6, and this also will be 6. And the numerator is going to be 120. The denominator is 120. So after simplifying, it's 3 over 10.
Hey, that's all I done. I actually got the right answer.
Okay. Yeah, let's redo the problem. First of all, you assume all the beans are different. Okay? At least the physical structure are different. And the microscope are different. Okay? They're different. You cannot have identical. So if you pick up 3, if you don't count their order, just put them on the table, okay? No order. Then just like pick up 3 students out of 10 to form a committee, right? So this is a formula, committee formula. Okay, 10 factorial over 3 factorial, by 7 factorial. So there'll be 120 different groups of 3 beans. Now, when you look at the 3 beans, you want to have 2 of them are red, other one is other color, either white or blue. Either white or blue. So you decided to do 2 steps to get 2 red beans, then other color. Beans in other color, 2 steps. To get 2 red beans, because order doesn't matter. So it's 4 factorial over 2 factorial by 2 factorial. Then you can pick up one of the other of the beans in other color. There are only 6 choices there. There are only 6 choices there. Okay. So So multiply them out. It's going to be 36 divided by 120. It's 3/10. Okay. So there are 10 boxes. Among them are 4 identical red boxes and 6 identical green boxes. Okay. Now, if you put them in a row so that no red boxes are next to each other, and how many arrangements can you make? Put them in a row so that no red boxes are next to each other. How many arrangements you can make? Okay. Red, green. Okay. So red, green, 6 box. How many here total? 10, right? So red box are not next to each other. A typical example is like this. Okay, you have a 4.
Or possible.
Okay. Anyone? Oh, it's getting cold. Okay, got it. How do you do that? This is a trick, okay? So when I'm going to do is I make a space because the boys cannot be sit next to each other, right? The red box, I call boys. Okay, red box. So green box here, green box. How many green box here? 1, 2, 3, 4, 6. Okay, I'm put a space here. Yeah, this is the way you have to think. In order to make no red box are next to each other. So that means you have how many space you're going to put. You have to choose one of the spaces, okay? So you have 1, 2, 3, 4, 5, 6, 7. So if one of these 7 places, okay, you're going to put the red boxes in those spaces, then no red box, no 2 red boxes will be next to each other. Okay, so you have to pick up 4 spaces out of 7. Okay, it could be red, could be that one, could be that one, could be that one, right? For example, right? If those 4 spaces selected and you put other, and then you are guaranteed, okay, no red box are next to each other. Okay, so that's 7 positions. You can pick it up. So the answer will be 7 factorial. You pick up 4, right? Then it'll be 3 factorial. Okay, so this will be the answer. Just equivalent to saying that you're going to pick up 4 out of 7 students to form a committee. Right? So the answer will be 35. So you have to change the way to think about the problem. Then you will see, oops, that's great. You can figure it out. Otherwise, it's harder to figure out the pattern even. Right? But here the boxes are identical. Another way you can do is it's really harder to figure out. Okay. Other ways. This I think is still the best way. So first of all, yeah, you line up these green boxes in a row, right? You decide to insert the red boxes, okay? But so 2 red boxes cannot be next to each other. So between 2 green boxes, you can only put the 1. You cannot put the 2, right? That's it. Then how many spaces between the green boxes or outside? Then you have total have 7. So you just needed to pick up 7 places, and that's it, right? And so you have 7. You pick up, so you pick up 4 out of 7. Right. Then you get 35. Okay, another similar problems will be a bit string is a sequence of the digits consisting only zeros and ones. Right? How many 12-digit bit strings contains no consecutive ones? All right, let's look at this problem. We're looking for the streets contain no consecutive ones, but it can contain contains consecutive zeros, right? Could be 1 0 0, right? 0 0 0. Something like that. And I'll just give an example like this. Just to make sure there's no twos next to each other. No ones, two ones next to each other. And this is one of the pattern. Okay, so what you have to do is you have to make sure there will be no ones, one ones, two ones, right? But if you have more than if you have more than the 8, think about it. If you have more than certain ones, then it's impossible that crowded. There must be two ones next to each other, right? So there's an upper limit for the number of ones you can have, okay? So it's going to be 1 0 1 0 1 0 1 0 1, right? 1. I think so. Okay, so the maximum number of ones will be 6. If it's 7, then two ones must be next to each other. Okay. So anyone has answer? Okay. Suppose k equals 2. How can you get that? Okay, you have 2 ones. 2 ones, then you only have how many zeros? 10 zeros. Okay, if you have 10 zeros, how can I put a 2 there? 2 cannot be next to each other, right? How can I put 1 there? So you have 10 spaces. Right? 11 spaces actually. You have 11 spaces. Right? Some are between 2 zeros, some are on the left hand side or on the right hand side. So there will be 11s, right? Yeah, so it's going to be 11 factorial divided by 2 factorial, then 9 factorial. So when k equals 3, you already 3 ones. How many zeros do you have? 9 zeros. And for 9 zeros, you have 10 spaces you can choose. Okay, so 10 factorial, you have to choose 3 fact and 7 factorial. Right? Then k equals 4. Then you have 8 zeros left. Yeah, then you have 9 spaces you can choose. So 9 factorial over 4 factorial over 5 factorial. And just keep it going. Like, okay? So eventually, you will get k equals, when k equals 6, you have 6 zeros left. Okay? 6, 1, 6 zeros. But for 6 zeros, you have 7 places. Okay, you can put 1 there. So this is going to be 1 factorial, 6 factorial, and 1 factorial. Okay? So my answer is just add them together. It's going to be, it is going to be 1 plus 12, you know, plus is the number when k equals 2. 11 over 2 factorial and 9 factorial. And the 10 factorial and 3 factorial, 7 factorial. Right? And so on. And 377. Cool. David, right? It must be David. Okay, the idea is still very similar to the previous problem. If you want to make sure they're not next to each other, just mark the spaces, available spaces for this 1 to get there, right? Yeah. So you mark the space. There's only 1 space between 2 zeros for the 1. Otherwise, if you put 2, and then just only 1 you can select. Okay. So yeah, between 2 zeros, you only can put insert 1. Insert 1, 1. Okay. Just number 1. Insert 1, number 1. Okay. But of course, there are some spaces, some places you cannot you put nothing there. So then 2 zeros will be next to each other, right? The positive 4-digit integers that use each of the 4 digits, 1, 2, 3, and 4 exactly once ordered from list to greatest. Okay, I want to know what is the fifth integer in the list. Okay, positive 4-digit integers. I use each of the 4 digits, 1, 2, 3, 4. So I can only write, right? Like a 2, 3, 4, 1, something like that. 1, 2, 4, 3. Okay, those are just examples. Right? So let's count. Okay, so they're listed in the order. So clearly, you know, these two groups will be, right? If you begin with 2, definitely it's larger than the number begin with 1. So actually you have 3 groups here. Okay, you have 3 groups. Okay, right? Then you just need to compare with each group. And how many of the numbers here in this group? There's 6. Because 3 factorial, there'll be 6. Right? Here also will be 3 factorial will be 6. 6 many integers. Total 12. So the 5th one must be here. 15th one. Right? Must be in the 3rd group. Right, so 15th one must be in the 3rd group. So you just need to begin with the 3 first. Right? So 3. Right? And then 1, 2, 4, right? 3. 1, 4, 2, 3. 2, 1, 4, 3. 2, 4, 1. I think this is all the 4 numbers you can have. And then, yeah, you can, that's right. So there are 6, right? You can list all 6. The others is going to be like a 3, 4, 1, 2. 3, 4, 2, 1. Right? So 6, 12, that's the 13th, that's 14th, that's the 15th. So 3, 2, 1, 3, 2, 1, 4 is the 15th integer.
That was pretty easy, honestly. That's okay. Gong, 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 gong.
All right, so now we have another type. Steve has 3 quarters and 3 nickels and 3 pennies. Okay, if Steve selects 3 coins at random without replacement, what is the probability that the total value is the exact 35 cents? Okay. All right. Right, we have 3/4, right? 3/4, 3/4. I'm not going to write on this. Okay, so in order to so you can see that how to make 35 cents, right? 1/4. The easiest way to do it is to 1/4 and 2 nickels, right? 25. So David, you think there's only 1 over 28? I got different answers, honestly. I think this is only combination 25, 5, 5, right? Any different answers? All right, so we're going to do the following. Think about this. So you have to figure out the denominator. Okay, the denominator is the number of all possible outcomes. You assume that all the coins are different. How about this? And you pick up them one by one and put them in the order. Okay, that's one way you can do, right? If you think, yeah, then how many How many possible outcomes? You have 9 coins there total, right? Put them in the order, right? In order. So 9 coins. And then you have 8 choices, then you have 7 choices. That's the number. That's the number of all possible outcomes. You do agree, right? Then the next is you're going to, all the coins are different, okay? Sometimes the value is different, sometimes itself, 3 quarters are different. Then you want to get 1 quarter 2 nickels. 1 quarter 2 nickels can be in the following order. Okay? Q and N, and Q N, and N and Q. Okay. For each pattern, right? How do you pick up a quarter, right? You have 3 quarters, so 3 choices. How do you pick up a nickel? It's three nickels and then 2 nickels left. Okay, so this is what. But you have 3 different format: Q and N, and Q N, and N Q. So you multiply by 3. Okay, so you cancel. Done. That's 3/28. Okay, right? Now you may say, okay, I just grab 3 coins. There's no order. If there's no order, I have to divide the denominator. I divide by 3 factorial. But the numerator, I have to be very careful. There was no order. Okay, so how do you do that? There was suppose if we do not count we do not count on the order, right? Okay, then the denominator will be, you just select 3 out of 9. So 9 factorial, 3 factorial, 6 factorial. Right. But the numerator, you pick up 3, right? Only 3, and 5. A quarter, right? 1 quarter, 2 nickels. So for the quarter, yeah, how many? That's 3 quarters there. 3 quarters there. Okay. And 2 nickels. 2 nickels. Since the order is not counted, so you just pick up 2 nickels from 3. So that's the 3 choices. Or you can write the 3 choices over, use factors. That's small numbers. Let's just put 3 there. Okay. So it'll be 3. That'll be 7, 8, 9, and divide by 6. After you simplify it, you will still get Yeah, 3/8, 3/28. It's the same result. The last one is about mass counts, okay? If the 10 letters in mass counts, MATHCOUNTS, so my question is, what is the probability? that MATCH will be spelled out anyway in the arrangement. All right, so think about this. I think you just need to figure out, first of all, okay, when you do the permutation, right, the number of all possible outcomes, right, is going to be what? How many letters there? Right, 10, right? Mass counts, the 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 factorial. And you also have 2 identical t's there, so 2 factorial. So this is this will go to the denominator, right? But the numerator is the trouble, right? You have to count all the possible the number of desired outcomes, but you know this should be together, okay? This should be together. Then there are many possible patterns. Okay, and so on. And for each of them, you have 5 letters you can permutate, right? So there are 5 factorial here, 5 factorial here, and so on, 5 factorial. Total, there will be 6. 6. Okay, so the numerator will be 6 times 5 factorial. The denominator will be 10 factorial divided by 2 factorial. After you simplify, it is going to be 2,520. Okay, so this is an idea. The probability is it's not easy to do that. Okay. So yeah, thank you. All right, so we're done. Today we focus on probability. Okay, I hope I will receive an email from you or your parents about which problem you have trouble, so I can discuss in the next class. Okay, so you will get a new homework assignment.